All right, people, thanks for joining the session. And I'm actually, while I've just switched off. All right, I think the mic is still on. Yeah.
Go back. We have this.
Wow, this was fantastic. So I just did a DOS, actually today already two on our own presentation. Anyway, this is about security, and the title is inspired actually by physics. We're saying multi-message security. I'm actually a physicist, and I used to work in multi-messenger astrophysics. So if you don't know what this is, it is about combining two things that are from different orthogonals or different verticals, where then the sum of the information, when you combine it, is much, much bigger, actually gives you a volume of information rather than combining two one-dimensional slices. And this is what we're going to do here. We have here two CNCF projects, one from two verticals, from security and from observability. Kubescape and Pixie, exactly. And what we're going to do is we're going to combine them, minimally modify them, and then create from that stack an adaptive eBPF-based security operations center, completely open source. And then we're going to do a almost live demo of a realistic rootkit detection. So this is not some hello world exploit thingy that we're doing. We're going to do the nightmare kind of thing. We're going to accidentally infect our own stack, our own security stack, and then we're going to find out how that happened by zooming in and zooming out. So, super quick. My name's Constance. I'm a key researcher, and just this morning I got some funding, so big thanks to all the funding agencies. And with me is...
Hello, everyone. I'm Dom. I'm a CNCF Pixie maintainer and co-founder and CEO at Cosmic, and I've been working in the eBPF space the last 4 years.
Hey, everyone. I'm Ben, co-founder and CTO at ARMO. Also maintainer of the CNCF project Kubescape, and spent most of my life both in the offensive and defensive security world.
Right. So before we get into this, so we're going to talk a little bit about Security Operations Center requirements in a nutshell, in like 10 seconds. What is it about? And then I'm going to bring up the stack of all these players. Where do they fit in? And why is the combination much more than the sum of its parts? And then we'll show you in a live lab, which you can take home. So this is a type of lab where we're not going to go through the demo, but we're going to let you demo it at home. It's free, and you can try it out at home, bugs included. And we're going to, exactly. We're going to, of course, interpret what we found and summarize of how this helps us increase the detection ability. That's one thing, but also critically it reduces the data volume that we need when we build such a stack. And that has implications on cost. Yeah. So in a nutshell, what does make a security operations center, a SOC, good? Well, first off, you want performance to be good. So the overhead, the impact on your resource requirements should be low. Then you want it to be cheap, right? Especially the data volume tends to kick here, so we want small data volumes. And then for the functional parts, the detection should be fast and the detection should be good. Well, you know, we could give dissertations on this topic, but we have 25 minutes. So having said this, these are our high-level requirements. And when I set out 2 years ago to create the Kubernetes Storm Center for Cloud-Native Threat Intelligence, I needed a detection stack. And I was looking a long time for the overall linearly scalable framework to orchestrate all of these probes and probings and the results of the probes. And this is where Pixie come in.
So for those of you that aren't familiar with Pixie, it's an eBPF observability tool for Kubernetes. And the three core principles it has is that it has auto-telemetry powered through eBPF, meaning you install it on your cluster and it automatically instruments your applications. It has this idea of edge compute, where it actually provides processing capabilities within its eBPF collector, so you can filter and transform the data where it's collected. And finally, it has a scriptable interface. And what that means is you can use its own data processing language to basically reprogram the UI and reprogram this data transformation. So coming back to how this fits within the SOC that we just outlined, the low overhead requirement pairs nicely with Pixie's eBPF autotelemetry. It means that we have this always-on system-wide visibility. The next two requirements, the small data volume and fast detection, Pixie has us covered because it filters and transforms the data on the edge. So you don't need to ship large volumes of data and then have to deal with storing and querying it downstream. And finally, the scriptable interfaces provides the ability to reduce these false alarm rates. We basically can deploy instrumentation on the fly and also filter it for what we need. And as we get into the demo portion of this, we'll see how that adaptive capability helps us handle anomalies.
Yeah, over to the anomalies. Back then, I was also building a detection stack, right? And the first thing you see is a lot of noise, so you need to somehow get rid of the baseline. And this is where Kubescape Node Agent comes in, Ben.
Yeah, so just like really a few words of introduction to Kubescape. Kubescape is a Kubernetes security platform that does all your security needs in a Kubernetes cluster, nearly all your security needs. So from posture, vulnerability scanning, configuration scanning, throughout network policies, SecCom profiles, and so on, to the Node Agent. The Node Agent is an eBPF agent that is evaluating rules. Rules are a way to create detections in the Kubescape world. So you have static rules where you can say that if there is a pod that is executing binary from the memory, it's a malicious activity. But beyond that, there is an ability for Kubescape to use BOBs, bills of behavior, that are describing what a pod is doing, like which processes can run in a pod, which network connections can a pod have. And through this description, any kind of deviation that happens during the runtime, Kubescape generates alerts. And these alerts can be captured through the SOC.
Excellent. So let's now build this out to scalability, put it together, and show what we can do with it. So first off, you would be choosing a Kubernetes of your choice. From OpenShift to EKS to Kind, pick something. And you'll have apps, your own apps. Those we ignore for now. And the first thing that we need to do is for all our components that we're running on these Kubernetes is that we have those bills of behavior, that we have a supplied profile of what we want the runtime behavior to look like. So then we install Kubescape Node Agent to do that diffing of the observed behavior versus the desired behavior. And that can give us a difference, not necessarily an anomaly, but it gives us a difference between what is actually happening at runtime versus what we thought should happen at runtime. And that makes anomaly a first-class citizen in this detection and is crucial to reduce the data volume because we're not just getting everything out, but we have an a priori filter. So this is what Node Agent does for us. Now, typically you would have an out-of-band storage the moment you have something suspicious. We use ClickHouse DB for this. For this particular demo, however, we're putting it inside the stack, and you'll see why in a second. And then comes in, of course, Pixie, the overall orchestrator for bringing in any reaction, reactivity, and adaptivity into the stack. So the first thing it does, it can talk to the ClickHouse shard, it can talk to our forensic detection, but it can also coordinate what happens after anomaly has been detected. Because, as we've heard, it can look back. It has a lot of default tables in which it stores 24 hours of debugging information, such as protocol traces, but as well stack traces and other information. So we can always look back and immediately enrich across the stack what happened with that particular anomaly filter. And the other really cool thing, and this is what makes it adaptive, is that we can on the fly compile new BPF probes into it. And so we have a compiler, and Pixie will distribute it out into the edge, collect the data in, and we can again enrich looking forward and have that smoking gun evidence that we were missing previously because we already knew, okay, we had a good idea, but now we know what really happened. And in the end, it's also important that we release all the probes again. Again, this is also part of the adaptivity, also to keep the system stable and to conserve space. We need to also release it. So the idea of adaptivity is we zoom into the anomaly, we enrich it, and we can zoom into the point that we either have to triage or we just don't know what happened and we give it to a human, and then we zoom out. And that's the idea of the adaptivity. Okay, that was a lot, so we're going to show you now IRL how this looks. And you can literally, it's all open source, you can completely look at it. So this is not a Hello World attack that we're doing here. We're doing a nightmare kind of thing where we have an IO Uring rootkit in one of our own database servers. The IO-Uring subsystem in the Linux kernel is a relatively new thing that is doing high throughput I/O asynchronously to the kernel, and this makes hiding very much possible because it's basically a queuing system where instead of writing each syscall individually, I can queue a lot of system calls, and thus they are not using the normal paths in the kernel, which is why oftentimes they're not naturally detected by EDRs. Naturally meaning you have to specifically look for them. Right, so what we're gonna do. So we had the ClickHouse HyperDX chart, and by accident, or divine design, it turns out that the app server is a Node application that uses IO-Uring. And it's very noisy, so it talks a lot. And, but the funny thing is that it looks tiny little bit different from that rootkit, and this is why we're hiding in that app server, mock hiding, of course, our rootkit. So we're gonna see now in the detection, we have noise, we have a lot of stuff going on, and we have a real application that actually already uses that syscall, so we cannot say, well, you could have blocked that whole subsystem anyway, which is a normal way of, we just don't use IO-Uring. This is the legal disclaimer here. We did not compromise the actual ClickHouse. ClickHouse is perfectly fine. Yes, it's a second process that we fake ignore. So that this is, this is not actually abusing anything. You can, this is already online. You can look at this lab. It's public. 1 hour per day playing it is free. Now I'm going to switch over to the lab. So I am going to not do it live because of time reasons. So you would come out here, you would start this lab on the left side, you would then install Kubescape in a specific configuration, make Kubescape. That would give you Node agent running and eBPF probes there. Then you would install a fork version of Pixie, custom built, including those SBOBs, including those fingerprints. So we would now have all the writing. And the last thing is we need ClickHouse, the database itself, and Vector for log forwarding. So that's our stack. Once that is installed, which takes about 6 minutes, now we would infect our stack. In this case, make update ClickHouse. And this is where our role play starts. So I'm going to be like the SRE who now executes make update ClickHouse and, well, finds or looks at the observational script that we have built in here in our SOC and looks at some of the noise that has been produced and like, okay, there's been an update, there could be noise, I might have to adapt my rules, my detection rules. And now what I see here is a couple of unexpected things. So those are anomalies. I see IO-Uring operations detected. This is a high priority alert from this application. And then I also see the IO-Uring register call is new. Well, we know that this Node application does use IO-Uring, so I'm like thinking, well, probably this register call is probably just
part of the new version of the package, yeah.
Yeah, it's probably just I just need to whitelist, allow listed it. This application profile, this SBOB looks like this. So it looks application profile, ClickHouse, and I see processes allowed. It's like, this is like Node stuff here. And these two syscalls, yeah, IO-Uring enter and setup already there, probably the register, they just have a new feature, right? And so what I'm going to do now is I'm just going to run the script, export like the pod, the namespace, and the command, and have this running. So I see, okay, this is the pod here. This is in this namespace click, and the command is called client. Well, this looks fair enough. So how dumb would I find out if that's really something I can allow list or whether it's something else?
So fortunately, because of this anomaly that was detected, Pixie has already started recording this data in our forensic database. But we also have the capability of inspecting it deeper so we can know whether this is a true anomaly or something we should be worried about. So now that that data is being recorded, looking at the flow diagram, we see that there is a bunch of DNS traffic, which seems normal. But we can look at, now we see these periodic spikes of network traffic, which seems a little strange. That doesn't seem like a common kind of database workload. So digging into the connection stats, that allows us to see the TCP data. We see a variety of connections being made. There's the DNS traffic that we talked about, but now there's this unidentified protocol 0. That seems a little strange.
Yeah, what can cause like Pixie not to identify these kind of protocols?
So this would mean that this is some type of either unsupported protocol by Pixie or some type of custom protocol, this application should be supported. So this is definitely not expected.
Yeah, so it's either like a problem of like, not tapping into something that in the communication, because it doesn't really make sense that the ClickHouse uses a protocol that PC doesn't support. Yeah.
No, it should be like HTTP based
Yeah.
or something, right? Can we find out what it's talking to?
Yeah, so we can actually Pixie can find out the metadata of that other side of the connection. So this pixel script here does just that. If we scroll down a little bit further, we can see that there is the client talking to kubedns, which we already knew. But now we see there's this C-Uring server. That seems weird. That looks like we're having an attack. Ben, what could we dig into to kind of dive deeper on the application side?
So, okay, let's do the following. So it would be nice to see, who's calling into this TCP connection, who's creating this TCP connection, who's doing the sends. So this is what we do. At this stage, what we are using here, can I click here? Yeah, so we are capturing over time the call stacks with Pixie of who's calling, what kind of call text we can sample, and it runs overnight. And we see that there is this IOU-ring enter call, and we see this call stack under that. And if we are going into, we're trying to create this expert, we see that we see here a lot of Go call stacks here. I don't know if you see the screen, but it's like really strange. Like this is a Node application. Why do we see Go code calling into IOU ring? Like this is like super weird and it shouldn't happen. And we look into the call stack and we clearly see that it's a Go call stack calling into this IOU ring system call.
Okay, so Go, so it was all Node.js, so this is pretty clear. But
Yeah.
we don't see anything yet. So we've got network and we've got this syscalls. Like hooking into syscalls is difficult, but could we maybe look at the VFS or maybe the Dcache to find out what it's writing?
While Pixie doesn't support that, cover that out of the box, it does have the ability to deploy on-demand probes. So why don't we do just that? Let's add a BPF trace script and look at the Dcache lookups.
While the application is running, right?
Well, yeah, while the application's running. That'll give us access to the files that this process is looking at.
So basically you're putting these K probes, so the C code in here, and Pixie's going to compile it live.
Mm-hmm. So after deploying that DC Snoop pixel script, we get a perfect view of what's happening here. We see this client command is reading Etsy Shadow. We see it accessing some Kubernetes service account tokens. At this point, I think we've nailed this down, that this is a nefarious process.
Yeah. So let me do a half recap and also some explanation, okay, what we've detected here. So as Constance explained before, so there was in our ClickHouse app, in the new version, through a supply chain attack, someone added a client application that wasn't part of the original ClickHouse release. This is the queuing client on this diagram that you see. This queuing client started up as a Go process inside the container, and it's used the IOU ring interface of the Linux kernel to disguise or hide its communication from detection tools, and started to connect the CNC service. The CNC service is, as you know, after it connected the CNC service, it returned the commands or pushed commands into the client. The client started to execute these commands. What were the commands? The commands were exactly reading those files. The DOM just showed you that reading the service account token, reading environment variables, host files, everything, and started to return this information to the CNC service. Now, the way we've detected this was twofold. One was the IOU ring register, which was the original anomaly that was a deviation from the Bob baseline behavior that we've seen before. Kubescape alerted on this. And then also, when we started to look into the actual behavior and used the amazing capabilities of Pixie to, in live, started to investigate how the application behaves, we started to find out that there were like nefarious connections to the outside world and these very, very strange file operations. So this is how it was detected. Yeah, so starting the wrap up here. So what we've shown you in this talk was an amazing SOC system with its amazing sensors that enabled us not just to detect some malicious-looking things, but also to, during the live running of the system, insert probes, insert extra capabilities to pull out information, so we can understand better what's happening here. We've shown that this system is adaptive, so we are noticing something, then we are pushing more capabilities into the sensor itself, so we can get more refined information back. And this enables us not to have upfront every logic inside the sensor, inside the system, just during the investigation at this overhead, the time after. And there is, as we see, these capabilities, this purely open source stack is as far as we know, unmatched even in the commercial world. So this capability. So, and beyond it also, the one thing we wanted to mention, the sensor in this case was a Kubernetes sensor, but it's not limited, the concept is not limited to Kubernetes, so you can have the sensor, the Pixie sensor as a Kubescape, you could have it also not in Kubernetes, but also on Linux host or IoT devices.
Perfect. Yeah, wrapping up, so we built out of two individual, very different, distinct projects, something together with minimal adaptation that let us see something pretty amazing. And the thing is that this lab was probably maybe overwhelming with all the scripts. And the cool thing is that there were 3 filters, right? And you could run all these scripts adaptively through it. So you are more than welcome to talk to us later if you run into any questions in that lab. It is completely open source. And you can, of course, also use your own detection logic in there. With that being said, there are booths. Please talk to us, connect to us. I'm an ambassador, so if you have any questions, also if you're a student and you want to do some research on this, we're very open to all of these things. Thank you so much. And for questions, please go to the microphone. Thank you.
Seems like it was totally clear.
No, there's somebody awesome.
Hi. So if I understood correctly, you can kind of include the probes that you can hook into on the fly of the application, which is really great. But also, are there any like the guardrails that will prevent the system from internal DDoS? If there are, like let's say some of the syscalls are just really overwhelming the system, if you have anything like this.
So there are no guardrails at the moment. So if you hook a syscall with a non-filter basic or non-filtering it, you will have the typical effect of flooding yourself. So cool. Unless, of course, PEM itself is memory limited.
It is memory limited.
Yeah.
I think we have the control plane mechanisms there to make it safer. I don't know that we've stressed it and tested those scenarios, but I think the mechanisms are already in place to like limit that. It just needs to be kind of like polished and invested in more.
Cool. And in the lab you were running some scripts, and you also mentioned, I think, that the scripts are like generated, or it's something that you need to it's a learning curve to learn them and run.
You can do both. You can write them, but they can also be prefabricated and trigger on the anomaly automatically. So we just pulled that out so that you would actually see how they trigger in those here docs. Yeah. Yeah, but so if you automate them, then you have exactly that problem that you might kick your system completely out of balance and completely DOS yourself. So with great power, right? So yes, I might also ask you for the microphone. Or yeah, this is actually.
Can you integrate Tetragon into this?
Yes, of course you can. Originally in the abstract, we had Tetragon in there. For time reasons, we left it out, actually, because we couldn't fit it into 25 minutes. But yeah, the full talk has Tetragon in there. Yeah, can be. You could put anything, yeah. Yeah. The key is that you have to write those adaptive rules that have to match and not kill yourself.